We introduce our work on spatial composition of 3D human motions for simultaneous action generation. Given a set of textual descriptions such as put hands on the waist and move torso left, our goal is to generate a motion performing these actions simultaneously, which we refer to as spatial composition. Current state-of-the-art approaches that combine motions from different captured actions involve graphic specialized pipelines who manually select the body parts of each captured motion to combine them. Our goal is to automate this process of creating compositional actions through an understanding of body parts. We observe that large language models contain knowledge about the correspondence between human actions and body parts. For example, when we prompt GPT-3 with what parts of the body are moving when someone is doing the action squat down, we obtain the legs are moving as a response. To exploit the knowledge of language models, we divide the human body into 6 body parts that relate to human action. To collect action part correspondence labels automatically, we use GPT-3 by constructing a text prompt that contains the list of body parts to choose from, and few short examples in the form of question-answer pairs, where the question is what are the body parts involved in the action, followed by the input action. Such labels enable composition of separate actions when they are compatible, that is, when the body parts involved in each action are disjoint. For example, actions stroll and raise arms are combined into a new motion here. This approach can be used to combine existing motions to create synthetic training data. It can also be used as a baseline to combine independently synthesized motions from a generative model. We call this new baseline single action GPT compositing. Since spatial motion composition is a new task, we propose 2 baseline methods based on a TEMOS motion synthesis model trained on single actions. First, we simply concatenate given actions with a conjunction word such as while at test time. Second, we introduce our GPT compositing to combine 2 independent generations together. For the inputs bring down arms and sit on chair, the single action model fails to produce the arm movement and only performs one of the 2 actions. Our new GPT compositing baseline overcomes this limitation. Our insight is that GPT compositing can augment real data with a rich source of compound actions. To exploit this enriched training data, we propose SINC, a text-to-motion synthesis model trained on simultaneous actions. The model architecture is TEMOS. The key is that we train on action pairs instead of only single actions, and we combine action descriptions into a single free-form text by randomly choosing from several augmentations. Equipped with our synthetic training data, this model learns to generate compositional motions. This learned model addresses the challenges that the single-action GPT compositing baseline faces. On the left is the ground truth motion corresponding to bend down at the knees and lift object with both hands. In the middle, we see GPT-based compositing of independent generations, bend and lift. The composition fails due to the fact that the global orientation is involved in both actions. The global orientation is taken from the bending action overriding the lifting motion. This is a common failure mode. On the right, it is our model trained on compositions, which performs both actions simultaneously. We also ablate the contribution of synthetic training by training our model on only real data consisting of both single actions and pairs of actions. For the input bend torso right and place hands on hips, training on real does not generate placing hands on hips, but our model generates both actions. Furthermore, we highlight the limitation of the existing APE metric based on coordinates. Our proposed TEMOS score better captures the semantics of this example, as it gives a higher score to the more accurate motion. Sit down while putting left hand on waist is an action pair that is not present in the training nor validation set of real motions. We observe that our model enables generation of out-distribution inputs because they are present on the synthetic training data. Move left leg in circles and spin arms backwards. Sit down and drink with right hand. Answer phone with left hand and sit down. Kneel down on right knee and tie shoelace. Finally, we qualitatively show the potential of our model to generate more than 2 actions. Kick with right leg, extend left arm, and look to the left. Squat, bend right elbow inwards and extend left arm. Thank you for watching.